Okay, hello advanced chemistry students. This is going to be a video that covers the extra practice for the extra dedicated student. Number one, convert a density of 13.6 grams per milliliter to its equivalent in pounds per feet cubed. So what we see here in this one is that we have units over units, and we're converting to units over units. So I call this a double unit conversion problem. And so what we're going to do is start out like normal, and we're going to go ahead and do our 13.6 grams, give a long T table, grams over milliliter. Okay, what I'm going to do first is I'm going to tackle one at a time. So let's do grams, and I need grams into pounds. So you would have to either look that up, or we would have to give it to you in the problem. So I'm going to go ahead and give it to you. 1 gram is 0.0022 pounds. Okay, so that one's done. Change colors. Let's do milliliters to feet cubed. Well, one major conversion in this class is converting milliliters into centimeters cubed. And that's key because it gives us length into volume, and sometimes that's a tricky thing to think about. Okay, next what we need to do is convert centimeters into feet, but we have this cubed function here, and so what we need to do is really be careful on how we tackle that. So what I know, and again, I would have to give this to you, or you would have to look it up, but I know that 2.5 centimeters is in 1 inch. And I also know that in every 12 inches, there's 1 foot. So that gets me the conversion I need. I'm going to draw my double finish line. But what students forget is that now that we have a cube term, anytime I do a conversion like normal, but it's cubed, I have to cube the unit, but I also have to cube the number. So it would be inches cubed, and I would cube that 1, which is still 1. And then inches cubed has to be on top, so it's going to be 12 cubed, and then 1 foot cubed would be 1 cubed. So the 1 centimeter cubed was already cubed. You don't have to cube this 1, but everything else from here on out, after you've done your normal conversions, you need to cube. Okay, so let's go ahead and calculate. Final answer that we get is 847.24. Now let's look at units for this first one. Let's see what cancels. Grams on top cancels. I'm left with pounds on the top, which is what I wanted. Milliliters started out on bottom, so milliliters cancels. Centimeters cube cancels. Inches cubed cancels. And we're left with feet cubed on the bottom, which is what I wanted. So my units would be pounds on top over feet cubed. Now, if I'm looking at significant figures here, what I would see is I've got 3 in 13.6. I have 2 in this 0.022 pounds. I've got 3 in this 2.54 centimeters conversion, but I wouldn't use the 12. It seems like that's a counting number that did not use any sort of scientific equipment. And so I can either round. I would allow 3, and I'd probably allow 2. So let's go 3. 847 pounds per feet cubed. If we used this conversion, then you could also round to 850, no decimal place, pounds per feet cubed. A mole of hydrogen atoms contains 6.02 times 10 to the 23rd atoms and occupies 22.4 liters. How many hydrogen atoms are contained in 25.00 milliliters of this gas? Okay, so let's start out with 25.00 milliliters, okay, of hydrogen. Now you may not know this, but it's actually H2, but that's okay. I would highly suggest always writing the number, the unit, and if there's a chemical species, write that too. There's not going to be anything on the bottom here because we're just starting out with volume. Okay, I'm going to go ahead and convert milliliters into liters. And then we're going to use that conversion that they gave us. 22.4 liters occupies 1 mole. Let me erase that. Occupies 1 mole of hydrogen atoms, H2. And you could get specific and say atoms there. And then 1 mole also contains, because it told us 2 conversions in that problem, so 1 mole of hydrogen contains 6.02 times 10 to the 23rd atoms of hydrogen. And I'm going to go ahead and stop, calculate. I get 6.71875 times 10 to the 20th. If I'm looking at rounding, I'll probably take this first number that has 4 significant figures. It's possible that I would allow 3 for these 2 numbers as well, so I would accept 2 answers here, but I would not use this whole number here, this conversion. So let's go 6.719 times 10 to the 20th, H atoms, H2 atoms, but just know that I would probably also accept 6.72 times 10 to the 20th, H2 atoms. Okay. What volume of hydrogen would contain 4.5 times 10 to the 18 hydrogen atoms? And then it says how many moles of hydrogen would this be? Okay, so first thing I need to do is go ahead and convert atoms into moles, and I'm going to use the conversion that they gave me in the first step. So 4.5 times 10 to the 18, let's call them H2 atoms or hydrogen atoms. And I'm going to go ahead and convert those into moles. 6.02 times 10 to the 23rd atoms of hydrogen is in 1 mole of hydrogen, H2, let's be specific. And so what I can do is go ahead and stop here and calculate to get moles. And what I get is 7.475 times 10 to the negative 6 moles. But if I'm rounding, I'd probably go ahead and use 2. Possible that we could use 3, but when in doubt, just use the first number here because it's probably some sort of measurement. 7.5 times 10 to the negative 6 moles. But then it says what volume. So I'm going to continue this t-table, and I'm actually going to do the next conversion. I'm going to say that in every 1 mole of H2, I'm going to use that conversion that they gave me in the last problem, 22.4 liters of H2. And I'm going to go ahead and calculate and get 1.7 times 10 to the negative 4th liters of hydrogen. I guess I should show you here. It's what you get in the calculator would be 1.6744 times 10 to the negative 4th, which if we're rounding to 2, 1.7 times 10 to the negative 4th liters of hydrogen. And again, if you use 6.02, I would be okay with that answer as well, as long as we're being cognizant of actually rounding these numbers. A molecule of hydrogen moves at a speed of 115 centimeters per second. How long will it take to travel the length of the football field? So I think most students, what would happen here is that they would start with 115 centimeters per second. But our final answer needs to be in time and time alone. So I would not start with a double unit like this, which we call a conversion factor here. But instead, we're going to start with 100 yards long, and I think this is where some students are getting a little tripped up. It's not impossible to start with 115 centimeters per second. You just got to make sure everything cancels out. But I'm going to go ahead and start with 100. 100 yards is the length that I'm trying to figure out how long it takes. Now what I can do, I need to get yards into centimeters. So 1 yard is 3 feet. And again, if you looked up a different conversion, perhaps you can find a different route. 1 foot, 12 inches, 1 inch, 2.54 centimeters. And I would probably go ahead and memorize that one this year because that is common. And then now that we have centimeters, I can go ahead and use 115 centimeters per 1 second. And what that does is that gets me from length into time. And just to go ahead and show you on this problem, let's cancel units, yards, top and bottom, feet, top and bottom, inches, centimeters. We're only left with seconds on top. If we were left with seconds on bottom, that would be an inverse, and that's not what we want. So if we go ahead and calculate the final answer, we get 79.513 seconds in our calculator, but we need to round. 100 only has one significant figure. Depends on what you're using here. Perhaps you use the 115, the conversion that they gave you, 2.54 perhaps. So when in doubt, pick the best number that you can, of course. Don't leave it all as, a huge number with a ton of decimal places. We're going to go ahead and round to 3 here. So I would take 79.5 seconds. 100 yards seems like a counting number, but perhaps you did go 1 sig fig. Well, if you did that, then your answer, would have to be 80. But if you put a decimal, then that's too many sig figs. So on that case, we would just have to do 8 times 10 to the 1 seconds, which gives us only one significant figure. So there's grace, but we need to make sure we're actually trying to round properly. Speed of light is 3 times 10 to the 10th centimeters per second. Express this in miles per hour. Okay, this is our double conversion to double conversion problem. This is the one we saw in first question. So let's start out here. We're converting 3.0 times 10 to the 10th centimeters per second. Now, when you have centimeters per second, remember that per second, that's 1 second on bottom of the t-table. So let's do our first unit. I'll use one color for centimeters, and we're going into miles. So 2.54, there it is, per 1 inch. And then we're going to go 12 inches in 1 foot. We're going to go 5,280 feet in a mile. Now, some of you know the kilometer, 1.6093 kilometers per mile. You could go that route too. That is not incorrect. 1 mile, that's where I'm stopping because we're in miles. Let me erase that. Okay, now that we've got miles on top, let's go ahead and focus on seconds on the bottom. There are 60 seconds on top, 1 minute on bottom, going into hours. So now 60 minutes in 1 hour. And I have to flip those units to make sure they cancel properly because seconds were on bottom. So let's go ahead and cancel units. Centimeters, inches, feet, miles. Is on top. We're going to keep that one. Seconds cancels bottom and top over here. Minutes cancel, and we're left with hours. So final units, we have miles on top over hours on bottom, which is what we wanted. Final answer in the calculator, we get 671080887.6. A lot of digits. We're going to round to two significant figures. I'm looking at the 3.0 from the beginning. So 6.7 times 10, if you count, that is times 10 to the 8th miles per hour. Okay, next problem. Sample of seawater contains 0.075 grams of sodium chloride per, keyword, per milliliter of solution. So what we have is grams per milliliter. How many moles of sodium chloride are there per liter? So what we're looking for is moles per liter. So this is a double unit conversion once again. So let's set up our t-table. And we're going to start out with 0.075 grams of NaCl. Perhaps you knew that. And that's per 1 milliliter of solution. We would never write grams per milliliter on top of the t-table. We have to split it up. So we're going to convert grams to moles, and then we're also going to convert milliliters to liters. So whatever you choose to do first is totally fine. I'm going to do grams because it's on top. I usually like to do the one on top first. It says that a mole of sodium chloride is 58.5 grams. So I'm going to use 58.5 grams of NaCl on bottom, and that's going to be for every 1 mole of NaCl on top. So I've done that. Now I'm going to go ahead and convert milliliters to liters. And remember, King Henry died unusually drinking chocolate milk. Milliliters to liters is a jump of 1,000. Now you have to know that there's 1,000 small milliliters in 1 bigger liter. Some of us mix that one up. Okay, now we can calculate. That's it. Final answer in the calculator, 1.28205 moles per liter. And with sig figs, we're going to go 2 and round to 1.3 moles per liter of NaCl. True story, moles per liter is called molarity, and we could actually write it as 1.3 capital M. But we will learn that in Unit 12, long ways away from here. Okay, last problem. A doctor orders that a patient receive 1.5 times 10 to the negative 3 moles of sodium chloride. The only solution available contains 1.00 grams per 100 milliliters of solution. A mole of sodium chloride is equivalent to 58.5 grams of sodium chloride. How much of this solution should the nurse give the patient? So what I'm going to do is start with this 1.5 times 10 to the negative 3. Set up our t-table. 1.5 times 10 to the negative 3 moles of NaCl. Nothing on bottom here. I'm going to use my conversion that I used in the last problem. For every 1 mole of NaCl, I have 58.5 grams of NaCl. Now you'll notice that it's flipped here just to make sure that moles are canceling out properly. And then what I know is that they told me that in every 1.00 gram per 100 milliliter solution, I'm going to write solution, that's how much sodium chloride is available in a solution. So what I'm going to do is look at what the units are doing. So far I've got moles canceling, grams canceling, and if I was super specific, I'd write NaCl here. I'm left with milliliters of solution, and that's what the problem was asking. How much of this solution, keyword, not just sodium chloride, should the nurse give? So I'm actually going to go ahead and stop here and calculate. I get 8.775 milliliters of solution, and if I'm rounding, I would go 2 significant digits. Final answer, 8.8 milliliters of solution.